In this video, I'll be teaching basic probability for machine learning. So probability, it's all about how likely something is to happen and assigning a number to that. The reason why that's important in machine learning is because machine learning is all about predicting some sort of outcome. And often what a machine learning model is doing is it's actually outputting the most probable answer to whatever input. So today we're going to go over just a crash course in probability, and we're going to look at different types of probability, such as joint probability, conditional probability, and then finally we're going to go over something called Bayes' rule. Let's first start with the definition of probability. So if I have some box over here. So this box is something that I'm going to call the sample space, or S. And what this is it represents all the possible outcomes. So all possible outcomes of something, of some experiment, you could say. Now inside of this box, I have different points. And each of these points is actually an event. So this is an event. And an event is a possible outcome of this trial. So it's a possible outcome. And I'm just going to say that an event, I'm just going to name it A. So, this specific event here is known as A. And what probability is, well, so I'm going to use P to denote probability. I'm just taking the probability of A. So I'm just taking the probability of some event and I'm assigning this to some number. So actually, let's take a look at an example. So how about a 6-sided dice, which a lot of people are familiar with, but it looks something like this. And each side, so it's a cube, and each side has a number on it. So that might be 1, 2, 3, 4, 5, 6. So that means, what are all the possible outcomes when we roll this dice? I'm going to use these curly brackets to denote a set, but the possible outcomes are 1, 2, 3, 4, 5, and 6. So in this case, S equals to the set of numbers 1, 2, 3, 4, 5, 6, because every single time I roll a dice, that's my experiment here, it's rolling the dice. These numbers, those are my possible outputs. Okay, so now each of these events in the sample space, I'm going to say, okay, 1 is a 1, 2 is a 2, 3 is a 3, and you get the point. So if I came back to this diagram, the sample space diagram up here, then I could add some more points. So this could be representing A1, A2, A3, A4, A5, and A6. So there's 6 possible points. So if I go down here and I say, what is the probability of A1? Well, A1 means A, my event, is equal to 1. So the probability of rolling this dice to be equal to 1. What is that value? Well, we know that this is a fair dice, right? And which means that every single side has an equal probability of coming up. So this probability of A1 actually equals 1/6. And the probability of A2 also equals 1/6. And all of the probabilities, so this probability of A6 also equals 1/6. They all equal 1/6. So these values over here, these are the probabilities that we assign to some event. So let's put this in English. The probability, probability of event A1 is 1/6. So that's what this means. It means the probability of event A1 is 1/6. That's great. So we're getting an introduction to probability, and that's what this course is all about. But there's so much more left to learn in probability, and that brings me to today's sponsor, Brilliant. Brilliant is where you can learn by doing, with thousands of interactive lessons in math, data analysis, programming, and AI. Each lesson on Brilliant's platform is filled with hands-on problem solving that actually lets you play with concepts, which is a method that is extremely effective for learning because you're not just memorizing, but you're actually practicing those critical thinking skills. And you can build up real knowledge by just doing a few minutes every single day. A great way to supplement these video courses is actually through practice problems on Brilliant's platform. Currently, Brilliant has just put out a lot of new data-related content. So there's Introduction to Probability, Predicting with Probability. It's perfect for learners of really any level to get started, myself included. What's really awesome about Brilliant is that you actually get hands-on practice with real data sets, such as ones from X, previously Twitter, and Spotify. And best of all, you can actually try Brilliant completely free for 30 days. Just visit brilliant.org/Kylie Ying or click on the link in the description below. And if you do decide to subscribe, this will give you 20% off an annual premium subscription. In order to qualify as a probability, this P, there's 3 conditions that it has to satisfy. So the first condition is that for every single event A, so for every A, the probability of A has to be greater than or equal to 0. So that basically just means that every single probability has to be non-negative. Because what does a negative probability mean? We don't really have a meaning for that. The second is that the probability of the entire sample space, so all of this, is equal to 1. That means that the probability of any of the events happening, well, that has to equal 1. And then finally, if we have many events, so A1, A2, etc., up to AN, so just n events. So if these are disjoint, the probability of any of the events happening, so that's A1 plus A2 plus, all the way to AN, is equal to actually the sum of all the probabilities. So all the individual probabilities. So probability of A1 plus probability of A2 plus probability ... of AN. So that's just summing up all the probabilities. Now, let's go back one step. What does disjoint mean? That basically just means that they don't overlap. So that means that another word for disjoint is mutually exclusive. And this means that A1 cannot overlap with A2. So in here, this is 0. Okay, so that means that they're disjoint when 2 events cannot overlap with one another. So in our dice example, can we roll a 1 and a 2 at the same time on the same roll? The answer is no. We can roll a 1 and then on the next roll we can roll a 2, but on the same roll it has to be a 1 or a 2 or a 3 or whatever up to 6. But we can't have 2 numbers at the same time. So that is an example of something that's disjoint. And now this here means that the probability that any of these events happen. So event A1 plus A2 would be the probability that these 2 happen. A1 plus A2 plus A3 would be the probability of these 3. So all of them would be this, which is actually just the entire sample space S. But we don't have to go all the way up to S. So what this is saying is that if these events are mutually exclusive, then the probability of A1 plus A2 plus whatever number of events is actually equal to the probability of all the events themselves added up. So in our dice example, the probability of rolling a 1 or a 2 or a 3 is actually equal to the probability of these individually. So probability of A1 plus probability of A2 plus probability of A3, which is equal to 1/6 plus 1/6 plus 1/6, or 1/2. Now that we understand basic probability, let's discuss joint and conditional probability. So the first one is joint probability. And joint probability is just what is the probability of two different events happening. So the probability of some event X and the probability of some event Y. So X and Y, they're the same as A in this example up here. They're just two different events. So event X and event Y. And this can be represented in mathematical terms with this funky U, upside down U thing, or a comma. So all of these just mean the probability of X and Y. Now, I'm going to use a 52 card deck for a lot of my examples. And in a 52 card deck, we have two colors. So we have black cards and we have red cards. And under black, we have spades, we have clubs, and under red, we have hearts, and we have diamonds. So these are the four different suits. Now, under each suit, we have 13 different cards. We have ace, there's no 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, right? So that's 13 cards. And under clubs, we have the exact same thing, so I'm not going to rewrite all of that, but ace through king, so that's 13 cards. Same with hearts, ace through king, 13 cards. And under diamonds, we have again ace through king, 13 cards. Okay, so this is a 52 card deck. Let's use this 52 card deck to show what we mean by probabilities. So I'm gonna draw a random card. Okay, so the probability that the card that I draw, let's ask, what is the probability that that random card is a black card? So there are 13 plus 13 black cards, right? So that's 26 divided by 52 total cards, which equals 1/2. Well, now let's say, what is the probability of drawing a card and that card being a 4? Well, there's a 4 here. There's a 4 somewhere in here, somewhere here, and somewhere here. So there's 4 4s in this deck out of 52, and that equals 1/13. Okay, but Kylie, where does joint probability come in? So now let's ask, what is the probability that we draw a 4 and it's a black card? So how many cards are there in this whole deck that equal 4 and are black? So again, we have the 4, some 4 here, some 4 here, and some 4 here. Well, these two over here, those are red. So we don't actually count those, which means that we have 1, 2 cards in our deck that are both 4 and black. So this is now equal to 2 out of, we still have 52 cards in the deck. So 2 out of 52, which equals 126. So that is what joint probability means. It means the probability of both of these things. Now let's move on to conditional probability. Conditional probability looks something like this. We have the probability of some event X with this vertical bar, Y. And now what this bar here means, it means given. So translating this means the probability of X, of event X, given given event Y. So that means that Y has already happened. Okay, we're already saying Y has happened. Given that Y has happened, what is the probability of X? So let's go back to our 52 card deck and let's first look at an example. So what is the probability of, let's say, hearts, right? Given that we chose a red card. So how many hearts are there? There's 13. Well, now we're only looking at this section over here because we're saying that we've chosen a red card. We're giving the reader some information. We've chosen a red card. So that means instead of out of 52, we're only limiting this to 26 cards. So the probability that we chose a heart, given that we already chose that this card is red, is 13 out of 26, or 1/2. Now let me ask you, what is the probability that we draw a heart given that we drew a black card? Okay, well, if we're looking over here, none of these cards are red. So let me erase that because we're not focused on this part anymore. None of these cards are hearts. So that means how many hearts are in that box? There's 0 out of 26. So the probability that we draw a heart, given that we already knew we drew a black card, that's 0. And now finally, what is the probability of a 4, given that we drew a black card? Let's go back to our example. Okay, we know we're still in this box because we drew a black card. And now how many 4s are in that box? There's, again, 1, 2. So 2 over, now how many black cards are there? 13 plus 13. So 26. So there's a 1 in 13 chance that we drew a 4, given that we drew a black card. And so this, you might actually notice that this is equal to the probability of the card being 4 and the card being black, divided by the probability of the card being a black card. So that actually brings me to the mathematical formula for conditional probability. The probability of X given Y is equal to the probability of X and Y divided by the probability of Y. So yeah, again, the probability of X given that Y happened is equal to the probability of X and Y happening divided by the probability that Y happened. This leads me to a really important concept in probability called independence. Independence means, are these two events related or not? Does one event happening affect the other event happening? So, for example, let's say that we're drawing cards and, I'm rolling a dice. Does the probability that I draw a 4 out of the deck change if my dice, rolls a 1 or rolls a 6? No, these are two different independent events. So to formally put this, something is independent, two events are independent if the probability of X is equal to the probability of X given Y. So this means that X and Y are independent. Why? Because the probability of X, well, here we're saying, okay, Y already happened, but the probability is not changing. The probability is still equal. So that means that there's no way that Y actually affects X, because it doesn't matter if Y happened or not. The chances of X happening are the same. So another way to write this would actually be the probability of X and Y, if that equals the probability of X times the probability of y, then these two are also independent. But this is a little bit harder to conceptualize why. Now that we understand joint and conditional probabilities, let's move on to explain a few other concepts in probability. So let's say I have my sample space S, right? And let's say that there's a few different partitions of this sample space. So I'm just gonna say, okay, over here I have this blue partition. I'm going to call this C1. And then I have, this red part, and I'm gonna call that C2. And then I have this purple part that I'm gonna call C3. And so let's say that, my event A is going to be represented by this chunk of the sample space. So this is A. Okay, so first I want to talk about something called the sum rule. Now let's say we want to find the probability of A. We don't know that number, but we do know a few different numbers. So let's say we don't know, what this total black space is, but let's say that we are given this chunk and this chunk and this chunk that's in yellow, that's you can barely see. But what it's saying is that the probability of A is equal to summing over these chunks and taking the probability of A and that chunk. So in other words, in our example, this equals the probability of A and C1 plus the probability of A and C2 plus the probability of A and C3. So that's effectively just summing up this green portion over here. Sorry, let me change a marker. Okay, let's use orange. Okay, so that means that we're summing up this section over here, and then this middle section here where the orange barely shows up, and then this section over here. And that's just saying that when we sum up these three sections, that equals the probability of this event space A, which looks really obvious from this diagram, but now we're just putting it into a mathematical formula. Then we have something called the law of total probability. Earlier, we actually said that the probability of X given Y, so that's a conditional probability, is equal to the probability of X and Y divided by the probability of Y. So we can actually rewrite this. So let's multiply by the probability of Y on both sides. Now the probability of X given Y times the probability of Y is equal to the probability of X and Y. And what we're gonna do in order to derive the law of total probability, we're just gonna plug this thing into this portion of that formula. So the law of total probability says the probability of A, sorry to change the letters on you again, but I'm going back to this probability of A here, is equal to the sum over all of those chunks of, the sample space, Ci, and then the probability of A given that chunk times the probability of that chunk. All right, so this is the law of total probability, and let's try to visualize that. Okay, so the probability of A given some Ci. So what that means is, what is this chunk here when we're looking at this section? So that this value here, that gives us the probability of A given some C1. And then the probability of C1 is actually equal to this green portion out of the total event space. So that's this green portion here, including that middle part. So the probability of C1 is equal to this portion here divided by all of that. So in this case, it's approximately 1/3, a little bit less than that. And now if you take that over this section and this section, then we can actually find the probability of A. Okay, again, it seems like this is a really roundabout way of doing that, so why would we even bother? The reason why we do this is because sometimes this is the information that we're given. For example, let's say that we're trying to measure the probability of doing our homework. So probability of doing homework. And now let's say that the probability of doing homework changes whether or not it rains or it's sunny outside. So if it's raining, then I'm more likely to stay inside, and the probability that I do my homework is 95%. Now, if it's sunny, that probability drops to 30%. Okay, and we also know that, let's say we live in California, and the probability of rain in California is equal to 15% of the time. On a random day, what is the probability that I am doing homework? So probability of homework. Well, I don't know the total probability of homework, but what I do know is I know the probabilities given if it's raining or if it's sunny, and I know the probability that it will rain, right? And so what this actually ends up equaling is the probability that I do my homework given the rain times the probability that it rains, plus the probability that I do my homework given that it's sunny times the probability of sun. And now this sun we actually know is equal to 1 minus the probability of rain, because either it's rainy or it's sunny. There's no in between. So that means that this is equal to 85%. And we know that probability of rain is 15%. The probability that I do homework given that it's raining, okay, well, that's 95%. The probability that I do homework given it's sunny, 30%. So now, I can all of a sudden solve for the probability that I'm doing homework on a given day. And that equals 0.95 times 0.15 plus 0.3 times 0.85, which if you plug that into a calculator, this comes out to 0.3975, or approximately a 39.75% chance. So 40% chance that I'm doing my homework on a given day. So cool. Would you have guessed that from these numbers? Probably not. But now with the law of total probability, we have a way to solve for that. And that's why this complicated equation over here is all of a sudden so useful sometimes. Now, given the law of total probability, I want to focus on something called Bayes' rule. So Bayes' rule is really important, probably one of the most important things about this specific lesson. So Bayes' rule is another way to solve for a conditional probability. It's another way to solve for probability of A given some probability B. And we know that this is the probability of A and B over the probability of B, right? We've already talked about that. And we also have a probability for A and B, right? And this can be the probability of A given B times the probability of B, which is not really that helpful for us, because if we use that, then we cancel these two B's and we're just left with probability of A given B equals probability of A given B. Okay, not very helpful. So let's get rid of that. But the probability of A and B is the same as the probability of B and A. So this is actually interchangeable, and we can write this as the probability of B given A times the probability of A. And now we can say, okay, the probability of A given B can actually be expressed in terms of probability of B given A. And all of a sudden that's really powerful because sometimes we don't know A given B and we want to solve for it. And we're given B given A. So this here is Bayes' rule. Okay, so what we can do is actually rewrite this, and then I'm gonna name a few terms. So let's rewrite this. Probability of A given B is equal to the probability of A times the probability of B given A divided by the probability of B. This here is what we call a prior. Okay, so before we get some evidence B, the probability of A, that's what we have. So that's what we know. That's our prior probability. And now this here, probability of B, this is called our marginal probability. And that means the probability of some evidence B, the probability that this evidence is occurring. This probability of B given A, this is our likelihood. So how likely is it that, this evidence is occurring, given that this event A, this belief is true? And then finally over here, we have our posterior. So this is our updated belief. This is our updated probability of A after some evidence of B. In machine learning, what actually happens is we're constantly updating this prior and we're getting a new distribution out of it every single time we see new evidence. And that's how probability ties into machine learning, is we're constantly updating what we think is true and the probability, we're constantly updating the probability of something to be true. And finally, before we finish this lesson, let's just do a quick example with Bayes' rule. Let's talk about COVID testing. Okay, when you have COVID, you can test positive or you can test negative, right? So there's two possibilities of COVID. So if somebody actually has COVID and someone who does not have COVID. Now, if I actually have COVID and I take a COVID test, I can test positive, right? And that would make sense because I actually have COVID. But I can actually also test negative, right? If I didn't wait long enough to take the test, then my symptoms or whatever, and the test comes back negative, even though I'm actually positive. So this is something called a false negative. Now, somebody who doesn't have COVID can also test positive, and they can also test negative. And when somebody doesn't have COVID, so they're actually negative, but they test positive, this is called a false positive. And in this specific case, test makers actually know what these probabilities are. In the case where, if we think about it, what is worse? Testing positive when you don't actually have COVID, or testing negative when you actually do have COVID? Well, if you test negative and you actually have COVID, and then you go around somebody, maybe your grandma, well, that's bad because the test said you don't have COVID, and now you may have just exposed somebody else to COVID. Maybe COVID is not that bad anymore, but let's say that it was some new mysterious disease that has a 50% death rate. Well, it's really, really bad to actually test negative because you don't want to be spreading that around, right? Whereas if you don't actually have it and you test positive, you just play it a little bit more safe. It's not the end of the world. So in this specific case, when test makers are making these tests, they actually prefer, they think it's okay to have a higher false positive rate than a higher false negative. So let's say that these tests, when you actually have COVID, they are 95% of the time true positive. So you actually have COVID and you test positive. And 5% of the time, okay, fine, you test false negative. Well, when you don't have COVID, they are okay with that maybe being a 90% negative test. And then when you test positive, that's maybe 10%. Okay, and then now at any given point, let's say we also have approximate estimate of how much of the population has COVID, how prevalent is COVID. And let's say that's 2%. So 98% of people actually don't have COVID. Okay, so suppose we test positive. What is the actual probability that we have COVID? And this is not knowing anything else. This is not knowing, oh, I have a cough and a fever and symptoms like COVID. No, right now we just know that we just tested positive. What is the probability that we have COVID? Okay. In mathematical terms, what we're trying to solve is the probability that we have COVID given that we tested positive, right? And now we can use Bayes' rule on this. So this equals the probability that we get a positive test given COVID times the probability that, COVID is actually a thing divided by the probability of a positive test. Okay, so let's look at our tree and solve for each of these. The probability that we test positive given that we have COVID. Okay, so given that we actually have COVID, the probability that we test positive here is 95%. So this here is 0.95. And then the probability that we have COVID. Okay, well, what is the probability that we actually have COVID? Here. So that's 2% times 0.02, because we have to divide that by 100. 2 divided by 100, 0.02. And now divided by the probability of testing positive. Okay. So the probability of testing positive, we actually have to use what we learned up here, the law of total probability, because we don't actually know straight up what is the probability of testing positive. We have it over here and over here. Let me get rid of a few of these circles first. Right, so we can test positive here and we can test positive here. So the probability of testing positive here is equal to the probability of a positive test given that, we do have that COVID, that given that we actually have COVID times the probability that we actually have COVID plus the probability that we're positive given no COVID times the probability of not having COVID. So the probability that we test positive given COVID, we already have that value up here. We already actually have this top part up here. That's our numerator. So I'm just going to copy that over. 0.95 times 0.02 plus, now this denominator here is just the other branch. So the probability that we test positive given that we don't have COVID is 10%. So 0.1 times the probability of no COVID is 98%. So times 0.98. And let me just move this part over so we don't, it doesn't intersect. Oops. Okay, so this here equals this. And now if we actually do the math here and do these multiplications out, we get 0.19 in the numerator plus 0.19 over 0.19 plus 0.1 times 0.98, so 0.098. Okay, and this actually ends up giving us around 66. So now, given that these probabilities are true, which, in the real world, they probably are not. This is just an example problem. But given that these are the numbers, if we test positive and we don't know that, we have symptoms or anything, the probability that we actually have COVID is only 66%. So yeah, that's Bayes' rule, and that's what a lot of probability is based on. Bayes' rule is often used for things such as statistical inference and modeling, and also it's used in different machine learning algorithms such as naive Bayes or expectation maximization. So it's really critical to have a solid foundation of probability. And so hopefully this video today has given you enough of a foundation to understand some basic probability concepts so that you can at least get started in machine learning.